Okay, let's just jump right in. When we think about chemistry, we usually picture what? Lab coats, bubbling beakers, maybe some crazy complex equations on a chalkboard. But what if I told you it's something way, way bigger than that? What if it's the fundamental operating system for our entire world? Seriously, from the air you're breathing right now to the phone or computer you're watching this on, everything, and I mean everything, is running on a set of these invisible chemical rules.
And it's not an exaggeration. I mean, just think about it for a second. Right now, as you're sitting there, your body is this absolute whirlwind of countless biochemical reactions. They're powering your thoughts, your movements, literally everything. So yeah, chemistry isn't just some subject that's in our world, it pretty much is our world.
Okay, so if we're going to stick with that analogy, if chemistry is the code, then what are its core commands, right? What makes it all tick? Well, believe it or not, a ton of the complexity we see all around us, it really just boils down to three fundamental principles. That's it, just three. So let's do it. Let's uncover these three core rules that basically govern all matter and all change.
All right, rule number one. This is maybe the most basic drive in the entire chemical universe. It's this constant quest for stability. See, individual atoms, they're kind of fundamentally restless. They're just sitting there in a high-energy state, and all they want to do is get to a more stable, lower-energy one. You can think of it like a ball perched at the top of a hill. It doesn't want to stay there, right? It just wants to roll down to the bottom where it's stable.
So the big question is, how do they do that? How do they find that stability? Well, they form chemical bonds. That's the secret. A bond is really just the force that holds atoms together. It lets them team up, you know? It's their ultimate solution to being so unstable. And this process, this is what creates the stable molecules that make up, well, everything. Water, rocks, you name it.
And it turns out, atoms have a couple of main strategies for doing this, kind of like a playbook. First, some of them form what's called an ionic bond. Think of this as a give-and-take relationship. A perfect example is table salt, NaCl. One atom literally just gives an electron to the other. Done. But then there's another way, the covalent bond. This is where they decide to share electrons instead. That's what's happening with the atoms in a water molecule. So you've got two totally different methods, but they're both aiming for the exact same goal. Just reach a more stable state.
Okay, that makes sense. Atoms bond to get stable. Got it. But what happens next? What happens when these newly stable molecules start interacting and reacting with each other? Well, that brings us right to our second rule, what I like to call the chemical tug-of-war. See, it turns out that most chemical reactions, they aren't just a one-way street. They're actually this dynamic two-way process.
And you see this all the time. Just think about the fizz in a can of soda. That's literally chemical equilibrium in action. There's this constant back and forth happening. You've got some of the dissolved CO2, the carbonation, escaping as gas, but at the same time, some of that gas is dissolving right back into the soda. Both things are happening at the exact same rate. It creates this perfect, delicate balance.
But here's where it gets really, really cool. This is the crucial part. We can actually manipulate this tug-of-war. We can push and pull it to get what we want. Let's take ammonia synthesis, a huge industrial process. On one side of the equation, the ingredients, you've got 4 gas molecules. But on the other side, the product, there are only 2. So what happens if we crank up the pressure? Well, the whole system tries to relieve that stress. And what's the easiest way to do that? It shifts the reaction to the side with fewer gas molecules, which means, bam, it produces more ammonia. This one idea, this one principle, is pretty much the backbone of all of modern industrial chemistry. It's huge.
All right, that brings us to our third and final rule. And honestly, this one might be the most important of all. It's simply this: shape is everything. The specific three-dimensional arrangement of atoms in a molecule, that is what dictates its properties. The way atoms are connected to each other isn't some random thing. It literally 100% defines what that molecule can do.
I mean, look, you want a perfect example? Diamond and graphite. Both of them are 100% pure carbon. Nothing else, just carbon atoms. But
their properties are worlds apart, right? One is the hardest substance we know, the other is in your pencil. It all comes down to shape. In a diamond, those carbon atoms are locked into this super tight, rigid 3D network. That's what makes it so hard. But in graphite, they're arranged in these flat sheets that can just slide right past each other. Super easy. And that's why it's soft enough to write with. It's amazing. Same atoms, different shapes, and you get completely different realities.
And this isn't just about cool minerals, okay? This principle, it is absolutely central to life itself, to biology. The function of the most important molecules inside of our bodies is determined 100% by their shape.
Just take proteins, for example. They start out as just a simple, long chain of stuff, amino acids, kind of like a string of beads. But that chain doesn't just stay floppy and limp. No way! It folds itself into these incredibly specific, intricate 3D shapes, like that elegant coil you see, the alpha helix. And here's the deal. If a protein folds correctly, it does its job perfectly. But if it misfolds, even just a tiny bit, it fails. It's useless. For a protein, shape really is destiny.
So, okay, let's step back and bring this all together. These 3 rules we've talked about, the quest for stability, that chemical tug of war, and the power of shape, they don't just work in isolation. You have to see them as part of this deeply interconnected framework, a framework that literally builds the reality that we all experience every single day.
Think about it. The quest for stability is what drives atoms to form bonds in the first place. Then, the chemical tug of war governs how those bonds break and reform during reactions. And finally, the power of shape is what determines the properties of whatever you end up with. From a single grain of table salt all the way to the impossibly complex double helix of our DNA, it all comes back to these 3 simple, fundamental ideas.
And that leaves us with a really fascinating thought, doesn't it? Because by understanding this code, by starting to master these rules, we stop being just observers of the natural world. We actually become authors. We become capable of designing new materials, new medicines, brand new technologies. So at the end of the day, the really big question isn't just what are the rules, it's what are we going to write next? What will we choose to create with them?